Today we're going to get into section 7.2, areas in the plane, and this is going to relate to some problems that we were looking at back in chapter 5, where we were trying to use the integrals to find the area bounded between a curve and the x-axis, but now we're going to take a look at what happens when our area is bounded between two different curves. So go ahead and carefully just copy down example 1. We want to find the area between the curves y equals cosine x and y equals sine x in quadrant 1, only to the first point, and this symbol here means intersection. So when you're done copying this down, pause the video and then graph both y equals cosine x and y equals sine x on the same coordinate plane. And we're going to go ahead and shade in the area we're talking about. So right here, this would be the first point of intersection. So it's bounded by the y-axis here and then the x-axis if necessary, but the area we're looking at bounded by these two curves in the first quadrant would be this area right here. So there's two ways to do this. The first way is, I'm going to just call it the old way. And that would be looking at the area of the shaded region is going to equal the area under, so y equals cosine x is above the y equals sine x. So it would be the area under y equals cosine x, so the area bounded by y equals cosine x and the x-axis. And then we would subtract, so imagine if we had to find this whole area right here, and then if we subtracted this area right here, we would be left with the green area. So it would be a subtraction. So the area under y equals cosine x minus the area under the curve of y equals sine x. So we'll go through it this way, and then we'll show you a more efficient way to do this. All right, so we're going to label this just as the area is going to equal, and then this will be where they intersect right here would be at pi over 4. That's where y equal, or that's where sine x and cosine x are the same. So it would be, first be the integral from 0 to pi over 4 of cosine x dx minus the integral from 0 to pi over 4 of sine x dx. So setting up is the key part here. Everything else, you're going to do this by hand. For some of these examples, though, we'll just set it up and type in the calculator. But for this one, let's continue by hand. So the antiderivative of cosine x would be sine x, as x goes from 0 to pi over 4, minus, and then this would be a negative cosine x, as x goes from 0 to pi over 4. So then this becomes sine of pi over 4 minus sine of 0. And we can say minus the opposite of cosine of pi over 4 minus the opposite of cosine of 0. Just got to be very careful with our signs here. So sine of pi over 4 is radical 2 over 2. Didn't mean to make theta there. It should just be 0. Sine of 0 is 0, so we can just cross that out. Then this will become plus cosine of pi over 4 is radical 2 over 2. Cosine of 0 is 1, so this will become a plus 1, and then this minus will turn it back to a minus 1. So we'll have 2 radical 2 over 2, so this just will become a radical 2 minus 1, and we'll say square units here, because we were asked to find area. So that wasn't too bad. But we don't always have to do that. Like I said, there's going to be a more efficient way. And if you actually look at the handout that I gave you of the flashcard facts, these are facts 38 through 40. And I just want to point out number 40 here. So it mentions the area between two curves, f and g, where f of x, just the curve sits above g of x, or if it's equal to, but it's going to be easier, obviously, seeing if it's above. It's just the integral from a to b of f of x minus g of x dx. So we're going to redo the problem, what I'm going to call the new way. And we'll see how this applies. But make sure you take a look at those facts, 38, 39, and 40. All right, so let's go back, re-sketch this. We're just going to go to pi over 4. And that fact for number 40 is also mentioned in a yellow box on page 375. Part of your assignment will be to write that down. So here we're just going to say the upper curve minus the lower curve. So we're going to just go from 0 to pi over 4 again. We could even use the property of integrals. So because we have the same limits of integration, we could have just wrote cosine x minus the sine x that was there. And that's what we're going to do. So the above curve is just cosine x. The lower curve is minus sine x, so we don't have to set up two separate ones. And then we'll have dx. And then just taking the antiderivative, we'll have sine x minus a negative cosine x. Again, as x goes from 0 to pi over 4. So this just becomes sine x plus cosine x. And we'll have the same. It's just we'll have sine x, or sine of pi over 4, plus cosine of pi over 4 first. Then it would be minus sine 0, this quantity here, plus cosine 0. We need to subtract both of them. So here we're going to get the 2 radical 2's. So just knowing both each of these will give us radical 2 over 2, so we'll just double that. And then this is where we'll get a minus 0 and then a minus 1. So we get the radical 2 minus 1 square units. Now we could check this graphically as well. So if you guys go to your calculator and graph both of these functions, and you can apply the window settings as I have written out here. Go ahead and pause the video and graph that. And just to clarify, to make sure that this is the point of intersection at pi over 4, go ahead and analyze the graph there, menu 6. Go to point of intersection. So the calculator, at least mine, is giving me a decimal value here, but you would just need to know that pi over 4 is equal to 0.785. You could just double check that. But just knowing our trigonometry facts, we would know that they're equal at pi over 4. So what you could do is go to menu. We're going to go back to analyze graph. We're going to go to 8 bounded area. At least it's 8 on my calculator. So the lower bound, we're just going to go 0. Upper bound will be pi over 4. And it should be giving us, so it's going to shade in as soon as you hit that. This should be the gray shaded region. And it's giving us that the area is a 0.414. And if you did the calculation of just radical 2 minus 1, you get 0.414. That's a nice way to check on the calculator, as we've been doing so far. But again, the only difference here is rather than our area going straight down to the x-axis, it's now bounded by some other curve. So it's just our upper curve minus our lower curve. What we're putting in is the integrand, what we're taking the integral of. All right, let's try a couple more. Here we're going to find the area of the region enclosed by these 3 lines. So pause the video to graph these 3 lines. So what's nice about this problem is we need to know the points of intersection. We can clearly see where the 3 lines intersect. And then this is the shaded region we're looking at. What's also nice about this example is it gives us a nice triangle. So there's 2 ways we could do this. We could calculate area just by using the formula. So we'll just say graphically, this would just be 1/2. Our base goes from 4 down to -8, so it's going to be 12. And then our height right here, which is perpendicular to our base, is going to be 4. So we're going to get 24 square units. But what if we wanted to set this up using calculus? We'll just say analytically. We wanted to find this whole region here. We're going to have the integral as we move from left to right is going to go from 0 all the way over to 4. And then our upper curve, the green line here, this is y equals 4 minus x. And then our red line here is y equals 2x minus 8. So our upper curve through the whole thing starts with the 4 minus x minus the 2x minus 8. So that's our f of x minus our g of x. We definitely want to combine our like terms here. So we'll get 4. We'll have a minus x minus 2x, so we'll get a minus 3x. Actually, let's just combine all the like terms here. Let's start back with the numbers. We have a 4 minus a -8, so we'll get 12 minus 3x as the simplified version. Take the antiderivative, we'll get 12x minus 3x squared over 2 as x goes from 0 to 4. And again, this one's nice to do by hand because our bottom number is 0, so we really don't have to substitute that in. It's just going to be 0. So we'll get 12 times 4, which is 48. And then we'll get 3 times 4 squared. So that's 48 over 2, which will give us 24. And then this turns out to be 24 square units, which matched what we saw up here. All right, so the idea is we want to be able to graph, find the points of intersection, because along the x values, as we move from left to right, those are going to be our limits of integration. Let's try one more. All right, so here's our two curves. So we have a quadratic, a parabola, and then we'll have a line. We want to find the area bounded by these two curves. So pause the video to go ahead and graph these. All right, so what we want to be very careful about here is the points of intersection. We have a nice one right here, but we need to know where this one is going to intersect precisely. So what we could do is just set both of these equal to each other. So let's find points of intersection here. I'm going to go ahead and just multiply the whole equation by 2. So we'll have a quadratic here. We'll bring this over. We'll factor this. So we see one point of intersection happens right over here when x is 4, and then the other one when x is -5. And even though, like, I didn't draw this perfectly, but I could see that it's going to line up pretty nicely there. So that's going to help us. So we're looking for this area right here. So we're going to set up an integral as x goes from -5 to 4. Now, one other thing that you might see to help you with some of your homework problems is symmetry. So if this was symmetrical and I could cut this in half, I could just double an integral. So be on the lookout for that. That's a nice way to start to work these out. So we could have the area would be the integral from -5 to 4. The upper curve the whole time is going to be 8 minus 1/2 x squared, and then minus our equation for our line, which is 1/2 x minus 2. Don't forget the dx. So we'll simplify this. So we'll start with the -1/2 x squared, then we'll have a minus 1/2 x, and then we'll get 8 minus a -2, so then we'll get a plus 10. And at least just for this example, let's just type this into the calculator, but you guys could go through the steps. You just get involved in some crazy fractions. So let's just do this on the calculator. So you should get 243 over 4, which is 60.75 square units. So those are some examples where we're finding the area of a region enclosed by more than just one curve in the x-axis. So we need to, again, look at where x is starting, where it's stopping, and that's mostly the points of intersection, or it could be the origin over to something else. So that's what we need to be able to make a sketch of our graph first, either algebraically to help us find the points of intersection, or at least the x values of the points of intersection. All right, so your homework assignment, make sure you correct yesterday's homework. Go back and look on page 375 at that yellow box. Know that fact. Go back to the flashcards facts as well. Make sure you look at 38 through 40. Try 4 of these area problems off of pages 380, 381. Go back to 372 to try a couple, and then try a few more AP practice problems. All of these are no calculator.